adversary lower bound arguments. How many people have seen this sum before? Okay, 1, 2, 3, 4, 5, maybe. We don't teach these at the undergraduate level anymore. Actually, some people have given up on any lower bounds at the undergraduate level. So, but the adversary, I don't know why. I guess there's just one additional level of quantification in what goes on in the adversary argument. So these are techniques which are generally more versatile and more powerful. They allow you to prove higher lower bounds over a much wider domain than the information theory arguments. And let me just introduce them by the game of Battleship. How many people have played Battleship? Okay, so I'm not going to get into the full rules of Battleship, but basically you have two people and they have boards that they don't see. Okay, so this is position 1, 2, down through Q, A through Z, 1 through Q, A through Z. And each player is given a set of ships. Okay, one ship has length 3, one ship has length 7, so I'm just making this up, length 2, length 4, whatever. And you get to place down your ships on the board, and the other person doesn't see where you've placed them. Okay, so actually, when I play this with my daughters, I always put them together. They just never seem to learn that. It really confuses them. Just to group them all together like that, because they're shooting all over the place. And anyway, so you get to put down your ships wherever you like, and then you take turns shooting at the opposite ship, so at the opposite board. So you would say, okay, I'm shooting at position 3, W. Did I hit anything? Yes or no? So this player would say no, nothing was hit. And this player keeps a record of what happened and so on. If they had said 3, C, then you'd have to report that something was hit, although you don't say what kind of ship it was. I'm really getting into more detail than I want to. The point is that when the player has hit all of the cells that ship is in, then you have to report that the ship is actually sunk. Okay? And the first person who sinks the opposite person's ships wins. Okay, is it clear how you play? Okay, so the right way to play this, I mean, the way that you play if you're honest, is at the beginning of the game you put your ships down, and then you start doing this volleying back and forth, and you of course report back honestly what happened. All right.
That's not how you play with your daughter.
Well, the dishonest way of doing this, if you can get away with it, it's very hard when you're physically next to somebody and they're watching what you're doing, is that you don't put your ships down at all at the beginning. Why should you commit yourself? Of course, as volleys happen, you have to give answers. Yes, you hit something. No, you didn't hit something. Yes, you finally sunk something. As long as there is a placement of the ships which is consistent with your answer, with your answers, you're alive. At the very beginning, there are lots of different placements of this ship. Why commit yourself to just one? As you go along, as long as you're careful enough to make sure that there's a placement of ships which is consistent with what you've said so far, you won't be detected as a cheater, and it's certainly better. You're keeping alive more possibilities, certainly a better strategy than to have put down your ships in the first place. All right? So what has this got to do with adversaries? An adversary argument is an argument that there is such a way of cheating. Okay? You're playing a game. The way to view this now is that the algorithm is playing a game against an adversary. The algorithm is trying to get the answer to its computation quickly. The adversary is trying to come up with input that makes the algorithm take a long time. Okay, so the adversary is trying to create input to make the algorithm take a long time. Okay? The algorithm is trying to get the right answer to a problem instance quickly. Now, what's the right way for an adversary to play? Should the adversary just make up some input and then let the algorithm compute against it? And then whatever time it takes, it takes. Well, that's the chump way of playing this. I mean, that's like putting down your battleships first and then playing the game. Okay? Because you don't know what that algorithm is going to do. You don't know what the opposite player here is going to do. You can't just think of one good input, one good way of placing down your ships that's going to be really good for any player you're playing against. And just the same way here, this adversary can't just think up one good set of data or one class of data that's going to force every algorithm to run long. But if the adversary can interact with the algorithm, see what it's doing as it goes along, and give answers to the algorithm. I mean, the algorithm is comparing two numbers and wants to know what the result of that. One number is bigger than the other, etc. So the adversary has to tell the algorithm something about the data as the algorithm goes along. As long as there is still possible input that's consistent with all the answers the adversary gave so far, then the adversary is alive. And if the adversary is clever about the way it feeds data to the algorithm as the algorithm is proceeding, then the adversary can force the algorithm to take a long time.
So the adversary has to know the nature of the algorithm, right?
The adversary is looking at the algorithm. Okay? The adversary is looking at the algorithm and interacting with the algorithm. Okay? It doesn't study the algorithm ahead of time, but it interacts with it as the algorithm, as a specific algorithm proceeds through its computation. It's asking the adversary about the input. Okay, the adversary hasn't given it all the input. It's just watching how this algorithm goes based on the input it's given it. And then for every question the algorithm asks, the adversary makes sure that the answer it gives is consistent with all the previous answers. That is, there is some input which would be consistent with all the previous answers and the answer that's about to be given. Okay? So that explains the algorithm and the adversary and how they interrelate. Now, who are we? Are we the algorithm or are we the adversary? We're neither. Okay? Well, we're the scientists. We're the people looking on the outside. To such a situation. Well, what we're interested in is proving the following, that there exists an adversary such that for any algorithm, the adversary can force the adversary through some clever means, which we have to explain, because we're proving this. We're proving that there does exist an adversary such that, given any algorithm, the adversary can force that algorithm to do some amount of work. And that some amount of work then becomes our lower bound. Okay? Now, I know this has been very, very general, but now I want to be much more specific. Any questions on the general framework? Okay? So we want to prove the following theorem. Any algorithm whose primitive operation is comparison of two numbers which finds the median of n numbers so we're talking about the median problem, which we've discussed, must do greater than or equal to 3n over 2 comparisons in worst case. Okay, so the problem we're dealing with is median finding. Given a set of n numbers, the algorithm wants to find the median of those n numbers. Its primitive operation is to take two numbers at a time and compare them. Is one bigger than the other? Which one? Or are they equal? And we have an algorithm which fits into that framework and does big O of n such operations. Remember, that's the big 5 algorithm. Now, we didn't work out any constant, and I don't know what that constant is. I have this number that's coming into my head of 17, but I really don't know if I remembered that correctly or not. But there is some constant on the number of operations, the constant in terms of the n for the big 5 method. It's 17n, say. Well, I don't know if that's true, but there are methods that are around 3 or 4n to find the median. And so in this lower bound issue, we're really concerned about what this constant here is. Here we're proving a 1.5n, which is still pretty removed from 17. There's a big gap between 17. There's even a big gap between 5 and 1.5. But nonetheless, this is good for illustration. And people have proven much higher lower bounds. They've been able to push this constant up. But the particular proof that I'm going to show you is pretty simple and illustrates what an adversary argument is. So everybody clear what this theorem is we want to prove? Okay, you have an algorithm that finds medians, and basically what it's doing is comparing two numbers at a time. We don't know what other logic it's doing, but that's the primitive operation. I could even formalize this a little bit, which usually we say the algorithm is in a black box here, and the adversary is over here. The algorithm doesn't directly look at the data. The adversary has the n numbers. And what the algorithm gets to do is specify two positions. Let's say it's in an array. The algorithm gets to specify two positions, and it gets to learn whether the number in position I is greater, smaller, or equal to the number in position j. Okay, so it gets back an answer. Right? And it's in such a framework that we're proving this theorem. This theorem says that any algorithm, when put in such a framework in interaction with the adversary, must do at least 3/2n comparisons. And how we're going to prove this is by proving there is an adversary that can create such an input for any algorithm. When faced with a specific algorithm, that adversary can create, by interacting with the algorithm, a list of numbers such that that algorithm takes at least 3/2n operations. The adversary is sneaky, as all adversaries are in this framework. It doesn't just create a whole list of numbers to begin with. It creates that list in interaction with the algorithm. And we, as the outsider, are able to prove that such an adversary can do that. All right? So let me get to the specifics. So here's the proof. Well, actually, there's a lemma that comes before the adversary, which is this. Well, before the lemma comes a description. So as the algorithm, or any algorithm, we have an algorithm that's interacting with the adversary or interacting with whatever is giving it these answers. As the algorithm proceeds, we represent the answers given it by a directed graph. So if the algorithm, for example, if the algorithm asks about the number in position I of the input and how it relates to the number in position j of the input, if it learns that this number is bigger than that one, then we'll put a directed edge from the bigger to the smaller. Okay, so this is input, well, the input of position I is bigger than the input of position j. We put a directed edge. Yeah.
What do we do with equal?
Okay, what do we do with equal? Two possibilities. We either go back to the definition of the problem and get rid of it by saying they're all distinct, or you might put in a bidirectional edge for equal. Okay, so we build up such a graph to represent the answers that have been given so far. The algorithm is asking about pairs of numbers, numbers in pairs of positions. It's getting back answers from somewhere, from the adversary, from memory, from looking at the data, whatever. And we represent what was given this way. And here is our little lemma. When the algorithm has found the median, when it actually finishes, and assuming the algorithm is correct, for any position or number I, there must be a directed path from the node for I to the node for where the median is. Let me do this in picture form. If the algorithm is finished, and it says, oh, I know where the median is. The median is in position 15 of the input. And I look at the graph that was generated. Oops. From, or to, sorry. Here's the median. And I look at the graph of queries that were done. What this is saying is that every node in this graph, each node represents a position in the memory, or the position of the input. Every node must either be able to follow a directed path to the median in this graph, or there must be a directed path from the median to that node. In other words, the explicit relationship of each number in the input to the median must have been determined by the algorithm. If we have another node out here which is like that, then you can look at this picture and say, no, the algorithm wasn't right. Okay, the algorithm, there's no path from this node to the median, and there's no path from here to there. So the algorithm couldn't be right. Okay? How do we prove this little lemma?
So if there is a path, that means the two numbers, the relationship between the two numbers is clear.
Yeah.
But is the converse false? If you don't have the path, does that mean that you don't know?
Well, we'll think about that for next time, and we'll prove this little lemma, and then we'll get into the actual adversary